So today I will give two examples of catalysis. So I have given a general idea or mechanism how catalysis works, like general catalysis. So today I will just show that two different type of reaction. One is acid-base catalysis. One will be acid-base catalysis, and second one is the most important one, enzyme catalysis. Okay, so how rate you can determine for these two type of reactions. So one is acid base and another is enzyme. So in acid base catalysis, first I will start with acid base, and after completion I will come to the enzyme catalysis. So in acid base catalysis there are few different types. So let's say for acid catalysis only. So one is specific, another is general. So in specific catalysis, there what will be specific? Only proton source, proton donor is required. Proton donor is must. So proton donors means I can say in general HA. So what is HA? HA is a acid. What type of acid that is? If it is a proton donor, if you remember, it's called Bronsted acid. Okay, so Bronsted acid means which is when some acid is required in a to carry out a reaction as catalyst, then is known as acid specific catalysis. Okay, and in sometimes acid is not required, like water. If you take or other source which is not actually an acid by means of donation of proton, water is like a, you can say it is like a general which can donate, but it is not actually, and by definition of acid you cannot say it is a acid. So this type of can act as catalyst, those are known as general acid catalysis. Okay, so in case of specific you must require a proton donor acid, and in case of general acid catalysis you don't require a specific acid. Similarly, if I say for specific base, if I say specific, then you must have OH minus ion. Okay, so if it is H plus, then for specific base catalysis you must have in the as catalyst OH minus ion, and if it is general, so any act as base general, then that can be general, just like acetate anion. So any negative charge species. Okay, so you have read in Lewis concept. Okay, Lewis base. So those are present, and if they catalyze the reaction, then it is general base catalysis. So hydrolysis of ester, that is a common reaction in organic chemistry. So those hydrolysis of ester reaction, in that case, a proton donor, then it is specific. I can write hydrolysis of ester. So in this case, you should have H plus as catalyst or OH minus as catalyst. So if H So this reaction, you should say it is, if H plus you are using as catalyst, then it is specific acid catalysis. And if you are using base as sodium hydroxide, potassium hydroxide as base to hydrolyze then that reaction will be known as specific base catalysis. So these are either H plus or OH minus. So you can see ethyl acetate and acetic acid. So like that you can have specific. Now for so general iodination of acetone. So if you take general acid, where you don't, if you have or you have solvent water, that will act as, so general acid catalysis reaction. The reaction is organic reaction mainly, CH3. If you want to do the iodine, you can have CH3CO CH2. You can use other than H plus donor as catalyst. Similarly, base catalysts are also there, general base catalysis. So these are, but you have to study the mechanism. Okay. So or kinetics you have to study. So example you should remember. So when it will be specific and when it will be general, I can show it from kinetics. Okay. So first I will, so in there are two different type of mechanism. So to show it is see from the PDF acid catalysis. So in you can have, so first I will show acid or base both you can show, but acid catalysis mechanism. Under acid catalysis there are two mechanisms. Mechanism 1, in mechanism 1 water take part in the reaction, solvent water. So you have substrate, then you have some proton donor, there is a reversible reaction. So from proton donor, that some acid, it will donate proton, and then that intermediate what will form in the next step, it will react with the solvent water and you will get product and H3O plus. Okay, so this is a mechanism where an acid is required. So that acid can be, I can say later, or I can show you later, that is general or specific. So first step is reversible. So you will have K1 forward reaction rate constant and backward is K minus 1, and in the second step it is K2. Constant means always small k. So from PDF, if you see, you make small or capital, but always it will be constant. Now intermediate is SH plus, whatever has formed, that which is reacted with acid and you got SH plus. So steady state approximation. SH plus. So what is steady state approximation? Rate of formation SH plus will be of consumption of SH plus. So rate of formation in step 1 SH plus is forming. So first step, if I, so it will be K1 multiplied by S into AH plus, and SH plus that in consumed means it is for two reactions. One is backward reaction, another is it is reacting with water product. So it is consumed in two steps. So in step 1 I can write K minus 1 SH plus into A, and another step K2 SH plus into water. Okay, so SH plus is participating in two different steps. Okay, so here water is solvent. So one approximation I can have that concentration of water, since water as solvent it is large in amount, so its concentration doesn't change. Water may, just like pseudomolecular reaction, so where solvent or catalyst that will present in the rate equation, but since its concentration will not change, I can think it is constant, and if it is constant I can ignore. Okay, so this is the approximation I can have, that concentration of water doesn't change because it is solvent. So your rate equation I can write K1 is AH plus K minus 1 SH plus A K2 SH plus. So now if I rearrange, then I can get the concentration of SH plus. That is the unknown here. So SH plus rearrange I can have. So I can take common first in the next step. Minus 1 A plus K2. So SH plus it will come out as K1 is AH plus K2. So now you have the equation. Now what is the product formation or rate of the reaction? So product formation I can write as, from according to the mechanism, rate for product formation. I can erase this. There is some network issue. I'm not sure how long it will continue. So rate I can write as dP dt, product formation with respect to time, and it is equal to the final step K2 into SH plus, because water is large, I can ignore that one. So your product formation will be K2 into SH. I already written from this equation, so I can bring that one here. So it will be K2 into KO1 is AH plus K minus 1 into A plus K2. Okay, so this is the equation I got. Now you can further rearrange. Okay, so I can consider two cases it can have from here. Case 1. So for the product formation. Now if K2 product formation step is much larger than the backward step, because I have written two-step reaction. One is intermediate to the backward reaction to the first step to the substrate. Another is SH plus, that intermediate can be converted into product. The product formation step rate constant is much larger than the reversible. So I can say the denominator I can write approximately 2. So I can write will be equal to K2 K1 AH plus. So I have ignored K minus A as compared K minus into A as compared to K2. So I can write this is K2. So K2 will get cancel out. The rate depends on AH plus. Okay. So in this case, you can see AH plus, I already told in the reaction mechanism that AH plus, initially what I have mentioned, this AH plus water or any proton source. So in the rate equation, you can see AH plus appearing. That means in that case, this can be water or any. This reaction, when the forward reaction rate constant is much larger than the backward reaction from the intermediate, then the reaction is general acid catalysis. Okay. Anyone is having any doubt? Can ask. In the first step mechanism, I told that AH can be water or it can be some proton source, just like Bronsted acid. Solution, you can see it is having AH plus. That means you don't have any water or any acid you can have in the rate equation. So in case 2, I can show that it will be opposite. That means when backward rate is much larger than the product formation rate constant. Okay, so then in that case, rate of product formation I can write as K2 is AH plus divided by, I am ignoring now K2 as compared to K minus 1A, then I can write it is K minus into K minus. Okay, now what I am doing, multiplying with numerator and denominator H plus. What is coming out? You can see in this case, if I consider AH plus whatever I have considered, that one is an acid, not any water solvent or anything. If it is acid, that will have a acid equilibrium constant K, So it can also dissociate as A into A plus, I should write not in concentration, I should write A plus H plus. So if specific acid, just like HCl you have taken, so that will dissociate as A plus Cl minus and H plus. So it will have some capital K. Okay, so capital K will be A divided by H plus. Okay, so you can see in this equation this part. So this thing, if you see that means it is together, then it will be 1 by K, because equilibrium constant, the product of the ions divided by the acid concentration. I can substitute these three things as capital K, because capital K equilibrium constant of that acid present in that equation. So I can, in this rate equation, when I have the condition that K2 is much smaller than K minus 1 into A, in that case you can have equilibrium constant of that particular acid. So in that situation, this type of reaction where K2 is much smaller than the K minus, this reaction will be acid specific. So this case, higher is the rate will be slow. Okay, so in the rate equation you can see that equilibrium constant of that particular acid is involved. So now this is becoming acid specific. In previous case that was not the case. So this is case 2. So in case 1 you can see there was no involvement of any particular acid, but in this case you can see specific constant of that acid is involved. So whatever you take, you can take H2SO4. Each acid will have equilibrium constant K value. According to that, it will change. Okay, it is present in denominator. That means higher is the K. So dilute acid will be much I can say opposite. Wherever K will be smaller, rate will be much faster. So if anyone is having question, otherwise I can move to the second mechanism.
No, sir.
Mechanism 2, I will just, you can, yes. Hello. So mechanism 2 is almost similar to the mechanism 1. So simple difference is, you can see from the PDF. I will not go again, then it will take a lot of time. The second type I will not have much time to complete. So in case of mechanism 2, acid catalysis only, 2 slide other than water, you should have basic. A base is also required, which can accept the proton product. Okay, so that type of reactions are also constant. Also, you can derive. Only thing, the AH plus whatever acid, you know that if you, let me say HCl, if you are taking, then it is H plus Cl minus. It is acid, its anion will be conjugate base. Okay, so that conjugate base we can write as just Cb. So in that case, that instead of water, that conjugate part, that is here A, so that will take the proton and give you the product, and in this case that AH plus, again it will be okay. So this is the only difference in mechanism 2, where water will not take part of the acid component, that is its conjugate base. It abstract the proton from the intermediate and it will follow the it will give you the product. So mechanism is almost. So rate constant also you can from here. In this case also you can see it will be giving you general acid catalysis. Okay, followed. So this will also lead to general acid catalysis. So same way you can see the base catalysis also. So just now I have discussed whatever the two part, both are based on acid catalysis. Any question? Otherwise, I will move to the important or most important topic, which is enzyme catalysis. So in enzyme catalysis, enzyme is a protein molecule. What is protein molecule? What is the structural requirement to be a protein? It will have peptide linkage. So all proteins are not enzymes, but all enzymes are protein, I can say. Okay, so enzyme is a biocatalyst. Okay, so in a body or in a biological system, different type of enzymes will be present. So all enzymes will not participate in reaction. So it will be reaction specific. So particular enzyme will participate in a particular reaction. So enzyme is a reaction specific. Just like if you have starch, you can convert into maltose by diastase or maltase. So maltose, if you have, you can convert into glucose by maltase. Similarly, if you have cane sugar, that is a common example, I can say. Sugar formula, you know, H22O11. So enzyme will be invertase. So invertase will give you glucose and fructose, C6H12. Both are having same molecular formula, glucose and fructose. Only functional group is different. One carbonyl aldehyde, another is keto. Okay, so So invertase is specific for conversion of cane sugar to glucose and fructose. Similarly, other catalysts are also present. So those biocatalysts are enzyme. It will work at some specific pH and specific temperature. So you can read those characteristic or properties of enzyme. What I will discuss, that is the most important. Okay, so enzyme kinetics is very important. And one first I will show, then I will write enzyme, how it will work. Do you know? It will work in lock key mechanism. What is lock and key mechanism? So can you open any lock with any key? So to open a specific lock, you should have a specific key. Okay, similarly, in a body, on a biological system, specific enzyme will specifically react with some specific substrate molecule. That is, means enzyme is substrate specific. Okay, so one can show this thing by a general, like your substrate is this kind of structure. So this is like schematic. Okay, having a chemical bond. Now you want to convert into this molecule and to this molecule. So that means you want to break the bond. So that enzyme will have some specific active site. Active site means it will have own reaction center. Okay, so when enzyme active site, this is known as active site. So I can say there are two active sites. These are the two active sites, and you can see active sites is exactly matching with the substrate structure. So this is substrate, and this is your two products. So when this exactly same or active site, when it is matching with the, then only they will start the reaction. And after the reaction, what you will get? You will get enzyme is again regenerated, and in the product you can see you are having the two thing, that chemical bond has been broken. So you now got the enzyme back and the product. Okay, so this is like a schematic. So this is known as where enzyme and substrate has reacted. So this is a complex. So this is known as enzyme substrate complex. I am showing in a single figure. This is known as when enzyme and substrate have bound each other. So then it is enzyme substrate complex, and in the final step you will have the enzyme back and the product. Mathematically, this is schematically I am showing. So this is just like in different book they will represent different way. So you can see the kinetics. If I write first step, what will have? You will have enzyme, then it will react with the substrate. Substrate is your starting material, and then you will have a equilibrium. Equilibrium in the sense just intermediate ES, and then ES will give you the product plus enzyme. So I can invoke here same concept, small k1 reversible k minus 1, and final step is K2. So first step is determining step. Second step is the first step where enzyme substrate converted into the product. Okay. So now write the concept steady state approximation, ES formation. ES is the enzyme. So formation is equal to rate of formation of ES. I can write from the first step into E into S. In the consumption step, there are two steps. One is backward, where ES is starting material and ES is converting the product, two steps. So K minus into ES and it is ES. So here one thing you have to remember, different from the other reaction. Here S here S is your substrate, E is your enzyme, ES is the enzyme complex. So when you have a enzyme is a large molecule. Protein molecule, you know, protein molecule is a large molecule. So in that case, my network is going to be not knowing. So I should have an equilibrium. Whatever enzyme you take initially, that will be, you have to consider, that is combination two term. So the enzyme initially, whatever, this is the initial enzyme and this is free enzyme. Free enzyme and this is substance. So whenever you have taken enzyme, so you are having reaction pocket in a enzyme molecule. This is one pocket, two pocket, three pockets. So all the pockets. So this is only one enzyme molecule I have shown. Let's say 5 pockets per enzyme molecule. So if you are having 10 enzyme molecules, the number of active sites or pockets are there. So the initial now 50, and now what we take, so out of 50, let's say this pocket is occupied, this pocket is occupied, so all the pockets may not be occupied. So out of 50, let's say 30 pockets are occupied. So whatever 30 pockets are occupied, that will give you enzyme substrate complex. So this 30 is enzyme substrate complex, and these are the free pocket, or this is the free enzyme, I can say. So there are 20 pockets. So 50 is the total concentration given by free enzyme plus enzyme substrate complex. Okay, so these things you have to keep in mind. So what E I have written in this rate equation is nothing but free enzyme. Okay, so in this rate equation, in place of E, you have to, because free enzyme, how much you have in the reaction catalysis system, you don't know. You know how much initially you are, how much substrate you have taken. According to that, you can estimate how much ES can be. But I don't know actually how much free will be there. So what I have to do, I have to with respect to E naught minus. So I will put in the equation in place of E, I will put minus ES. Now other terms are same. The handwriting is going very bad. So now what you are seeing, equation is little changed, and what you have to get, you have to finally rearrange and you have to get the intermediate, how much ES, that bound complex it will be. Okay, so if you rearrange, you will find it will be Q1, no, K2 will not be there, sorry. It will be E0 0 into S, K1 into S plus minus 1 plus K2. Oh, fine. So the rate of the reaction will be, so rate of product formation is final step. Okay. So rate of product formation is S. So now ES value you know, complex concentration you know, now you put it. So you will have K2, K1, E0 S, Q1 S, Q1. Now if I rearrange the equation, just like if I divide with K1, then I will have 2 E0 S, and you will have S into ratio of K minus K2 divided by K1. Okay, so for the page, my net is going to be finished today, so I don't know. So you can see that rate of the reaction is given by K2 into E0 into S in divided by S plus K1. So that part, so this right hand side, this term, these three things together, that is plus K2 K1. So this is known as Michaelis-Menten. Menten may be different from according to different book. I can replace here that you have to understand. So in the have rate equation. I will have K S divided by S plus Km. So what is Km? Km is K minus 1 plus K2 divided by K1. Okay. So this Michaelis-Menten rate constant, you can have idea what is that from estimation. Okay, so let me go first. Now let's say you have substrate, concentration of substrate, that means your starting material is large. Whatever substrate you will be taking, that will be converted into ES. Okay, so I otherwise I can say I can say this not according to substrate. If you are having lot of substrate, then if substrate concentration is large, substrate is in large quantity, then what will happen? All the enzyme will be completely bound with the substrate. So you will not have any free enzyme. Okay. So whatever initially enzyme you will take, that will be completely converted into enzyme substrate complex. Then this free enzyme E, that will not be there. So when substrate amount is large, all the enzyme pocket will be converted into enzyme substrate complex. E not equal to ES. So I can say that in that situation, when all the enzyme pocket has been converted into enzyme substrate complex, so I have erased. So rate equation, normally how you can write the rate of product formation. If you remember, I told rate will be K2 into ES. So when all the enzyme pocket is converted into enzyme substrate complex, then I can write this is the maximum rate, because physically you can understand that complex, then you have the maximum probability to get the product. That means the product rate of product formation will be large or maximum when ES is maximum. ES maximum means K2 into E naught. Okay, so K2 E naught is the maximum rate I can consider. Okay, so maximum rate I can consider when all the enzyme pocket has been converted into enzyme substrate complex. So I can say K2 into ES, this term, or K2 into E naught, this term is my maximum rate. Okay, so in this rate equation, K2 into E naught, so I can say this is maximum velocity, Vmax. Hello.
Yes,
Yes. Network 0 it is showing. So in the rate equation, I can say this K2 into E naught term as maximum rate. Okay,
sir.
so I'm not sure net is working or not.
Sir.
Yes.
Sir, your screen is
Hello.
small. Sir, your screen is small.
Okay, so might be network is my net balance got over or what? From yesterday, some problem is there. Hold it for a few minutes. I will just. Hello, so little bit is left out, so network is trouble here for last 2 days. Okay. So I am disconnecting and again I am connecting within 2 minutes. Just let me complete within 5 minutes. I can complete the last topic.